Okay, so in this video I want to talk about one of the identities for matrix-matrix multiplication, the transpose identity. We're going to go through a lot of sort of the properties of matrix-matrix multiplication, and for the most part I'm not going to prove anything about any of them. I'm not going to prove the facts. We're just going to kind of go through. But I wanted to prove one just to sort of show the flavor of what it's like, and I wanted to pick what I think is the most interesting one. Which is what happens if you have a transpose after a matrix multiply. What if anything can we do with that? And so before I get into the proof itself, I want to just sort of like have an intuition in my head for what I think should happen, right? And so let's say I have some matrices A and B, right? And one thing is that in general, when I'm doing these kind of proofs, I want to, or when I'm working with matrices in general and just like thinking up examples, which is more what I'm doing right now, I want to try and pick non-square matrices when I can, just to make sure that I'm not accidentally proving something that's only true for square matrices or only thinking about the square case. So I want to try and pick different sizes here. So I made A, mostly sort of squarish, but now we'll make B. Let's see, it's got to be the same. This dimension has to be the same, but we'll make this part short. So it's not a vector, but it's kind of like a tall and skinny matrix, right? So here's my A, here's my B, and now in here I have my A times B, my product, right? And then the question is, I take the transpose of that, right? Whoops. So again, this is part of where it's nice, especially with transposes, to sort of have it be not square, because I want to think, okay, AB transpose, it's going to be flipped, kind of flipped over, and it's going to be, instead of tall and skinny like B is, it's going to be more wide and short, right? Like that. And then the question is, can I describe this guy? I'm actually going to see if I can just like move this. Whoops. I'm actually going to see if I can just like move this thing over just a smidge here. Yeah, there we go. Can I describe this guy somehow in terms of A and B is really what I want to do. And so if I think about like, okay, if I pick some element somewhere in A times B, I know I said that that's the inner product of this column of B and this row of A. And when I transpose, it flips it along this diagonal here, right? So so that one ends up over here somewhere, right? And if I'm gonna get this shape, I'm gonna have to flip A and B also. So I'm gonna have to end up with something like, I'm gonna have to put the B over here to be B transpose, right? And I'm gonna have to get the A transpose over here somewhere, so that now that individual element that I picked out is like this row of B transpose and this row of, or this column of A transpose. And so the identity that I'm going to try and prove here is that AB transpose is equal to B transpose A transpose, like that. They sort of flip. And the units on this check out also. So if A is M by N and B is N by P, right? Then I know this whole the AB product then is M by P, right? And because transpose flips it, AB transpose needs to be P by M, right? So B transpose flips the B, so it's P by N. And then A transpose flips the A, so it's N by M. And it works. My inner dimensions line up, and my output is P by M. So the dimensions at least work out that the way that I have it written here. But of course that's not a proof that this is true. What I need is to somehow show that it's true for any matrices, A and B, right? And so for that, what I'm going to do is I'm going to prove that every element in this matrix is the same as every element in that matrix. Every element in the matrix I get by doing the left-hand side has the same value in the same place as the right-hand side. And for that, I'm going to need to use my definition, my sort of algebra definition of it. So remember we said if you have some matrix Cij, it is the sum from k equals 1 to n, and this I should say is for all I and j. Let's make it a little more. This is for all I in 1 to now I need to make sure I get it right. That's the rows, right? M and j and 1 to p. Did I get that right? Looks right to me, I think. Okay. Okay. So Cij is the sum across from k equals 1 to n. I just realized I wrote that wrong. Of A I k B k j. So that's fact number one that we're going to need, is this this definition of matrix multiplication. And then the other fact that we're going to need is the transpose. So for any ij, a transpose of ij is equal to a at ji, right? Just flipping the indices there. Okay, cool. So now we're set. So now we can say what I'm going to start with the left hand side of it here, right? So so A times B transpose at any index ij is going to be equal to this guy. Grab all this stuff. Yep. That's just our regular A times B product. But then this whole thing has to be transposed. So what I need to do is I need to swap the j and the i's, right? So so this is going to become a j right here, and this one is going to become an I, like that, right? Because of this fact. So just combine those two pieces, and I get sum of ajk bki, because this thing is equal to a times b ji, like that, right? So, okay. And then each one of these scalars, so this is AJK is a scalar, BKI is a scalar, right? So I can reorganize those, no problem. So this is going to be equal to the sum across K of B Ki A JK. And because transpose flips them, that's going to be equal to the sum of B transpose IK A transpose KJ, which is the definition of the product of B transpose A transpose. So that's equal to B transpose A transpose at IJ, right? So I should have done this a little bit. This is not, hold on. Actually, let me, okay, I just cleaned up my kind of awkward transition there, but okay, so A times B transposed at IJ is equal to A times B at JI. Now we use this definition of the sum, AJK, BKI, flip those around, and we get B transpose A transpose IJ. So, not super complicated, I don't think. But in general, I think these kind of proofs tend to be a little more tedious than anything else. Like, it's just kind of a pain to keep track of all of the indices and make sure that you're getting them all right. I hope I did get them all right in this proof. But I wanted to give a flavor. Like, it's really not hard to prove these facts that are true. We just don't go through it usually because it takes some time. This one I picked because I think it's the more interesting of them. And it's worth, hopefully this will also sort of hammer into your head the idea that you do have to flip them if you move the transpose through. And so now I can take away this big question mark here. And we can write there what it is, which is B transpose A transpose. Beautiful. So yeah, so that's our proof of this identity. Like I said, most of the others are pretty similar. It's good practice, and if you're ever thinking like, well, I need some more practice, one thing I think is like students can never get enough practice problems. At least there's some kinds of students who will always come to you and say like, I need more practice problems. Give me something else to work on. Go through and do this kind of stuff. Like, it might seem tedious, but go pick a different one, like the associativity of matrix multiplication, or the matrix addition identities, and just try and prove it for yourself. It will teach you. It will give you just more practice, being careful with the indices and moving them around and paying attention to what's what. So I think that's always good stuff to practice. All right.